Hello student, my name is Nimesh Prabhakar. I am Assistant Professor at LJ Institute of Engineering and Technology in Instrumentation and Control Department. Welcome to Process Control Lecture Series. In this lecture, we discuss about nonlinear system. In my previous lecture, we discussed about first order system. That system was linear system. In this lecture, we discuss about first order nonlinear system. But before start this, we understand the step for determining the transfer function for a process. So there are different steps. There are few steps to determine the transfer function of any system. So first step is write the appropriate balance equation. So by using conservative law, we write the mass balance and energy balance equation. So this is the first step. Then second one step is linearize the term if necessary. That means if any nonlinear term present in equation, then we have to linearize that term. This is the second one point or second one step. Then third one is place balance equation in deviation variable form. That means introduce deviation variable and write equation in deviation variable form. Then fourth one step is Laplace transform the linear balance equation. That means we have to taking the Laplace transform of that equation. Then last one step is solve the resulting transform equation for the transfer function. That means find out the output upon input or in the form of last one transform. So these are the basic steps for determining the transfer function of any process. Okay, now we move nonlinear system. But before we understand nonlinear system, first of all we understand what is linear system, and then we will understand about the nonlinear system. So first of all question is what is linear system, or in other words, which system is known as a linear system. So a system is said to be linear if all the functions in the equation are linear function. That means we write mathematical equation of that system and all that terms in that equation must be linear. So that system is said to be linear system. In other words, a system is called linear system if that satisfy these two conditions. That means homogeneity and superposition property. That two properties satisfy, then we said this system is said to be linear system. If any system satisfy these two properties, homogeneity and superposition, then the system is said to be linear system. Now what is homogeneity and what is superposition? Now we understand. This is the example for the superposition and homogeneity. Suppose we have one system and we give input x of t as a input. Then we get y of t as a output. Sorry, x1t as a input and we get y1t as a output. Then in another system, x of t is the input and y2t is the output. We get y2t as a output. Then in the system we give merge input. That means we give x1t plus x2t as a input. Then we get y1t plus y2t. That means the sum of output of this individual system. Then that system is known as linear system. Sorry, that system satisfy superposition condition. So this is the condition for superposition system. That means if we give individual input x1t, merge input x1t and out x2t, then we get merge output of these two systems y1t and y2t, then this system satisfies the superposition theorem. And the homogeneity theorem is, if system input is x1t and output is y1t, then that system is known as a homogeneity if we give a x1t as an input and we get as the output a y1t, then that system is satisfied the homogeneity property. So if any system satisfies these two property, homogeneity and superposition, then that system is known as linear system. And in other words, if any system that violate one of two properties, then that system is known as non-linear system. That means if system not satisfy any one of two property, that means not satisfy homogeneity property or superposition property, then this system is known as non-linear system. Okay. Now for better understanding, we will take the one example as a graph. So in the graph, in the left hand side, the graph is represent the linear system or linear function graph, and in the right hand side, this graph indicate the non-linear system graph. See here, the input and output is follow linear relationship, but here input and output that not follow the linear relationship, that follow some type of relationship. Here see, input and output follow the linear relationship. So this is a linear and non-linear system. Okay. Now to understand, we take one example of non-linear system. So this is the first order non-linear system. In this system, we take same example we taken for the linear system. That means we take the example of a water tank. In this, same as A is the uniform cross section area of tank, R is the flow resistance of tank, then V is the volume of tank, and rho is the density of material, that means the density of water. Q0 T or Q0T is the output flow rate, Q is the input flow rate, and H is the height of the water level in the tank, same as the linear system we taken. Now the relation between the Q0 and H, Q0 this output and the height in the height of water in the tank. So here is changed. This relation is Q0 is equal to C into H raised to 1 by 2. So this relation is a non-linear relation. In previous lecture we discussed about linear relation. In that Q0 is equal to H by R. That means H and Q0 is proportional linearly. But here Q0 and H is not satisfy the linear property. That means here Q0 is proportional under root of H, and here C is represent the constant. Now here the aim is same for the linear system as non-linear system. Here aim is to determine the transfer function that relate the height to flow. That means we have to find out the transfer function. So for this we take conservation equation. So from conservation equation we can write rate of flow in minus rate of flow out is equal to rate of accumulation of mass in tank. So rate of flow in is equal to rho into Qt, and rate of out is equal to rho into Q0T, and the rate of accumulation is nothing but the d by dt into rho into V. But we know V is equal to A into H. So we can write this equation as Qt minus Q0t is equals to A dH by dt. Now, from equation number 0, the value of Q0 is putting in this equation. So, for this equation, we put the Q0 is equals to C into H raised to 1 by 2. So, we can write equation number 1 as Q minus CH raised to 1 by 2 is equals to A dH by dt. Now, here non-linear term is present. This is. So, we cannot proceed for the Laplace transform, because for Laplace transform it is must in equation no non-linear term is present. So, first we convert this non-linear term into linear term. So, for this we use Taylor series expansion. The function of Q0t may be expanded around the steady state value h of s. So, thus we can write by using Taylor series Q0t as a Q0 is equal to Q0 h of s plus Q0 dash h of s, hs, h minus hs plus Q0 double dash hs, h minus hs square by 2. Here the Q0 double dash. So, in this equation, Q0 dash is represent first derivative of Q0 and Q0 double dash, this represent the second derivative of Q0. Now, if we keep only linear term, the result is, that means in this equation we keep only Q0 dash term, Q0 double dash term we not keep, only linear term we keep. So, we can write Q0 is equal to Q0 hs plus Q0 dash hs, h minus hs. Now, we give this equation as a equation number 3. Now here we require Q0 dash, that means derivation of Q0. Here we know the Q0. So, we have the relation equation of the Q0. So, from that equation we can write the Q0 dash, that means we have the value of Q0 is equals to C into H raised to 1 by 2. So, from derivation of this equation with respect to H, we get the value of Q0 dash. So, we can take the derivation Q0 dash Hs is equals to 1 by 2 CHs raised to minus 1 by 2. Simply, the derivation of CH raised to 1 by 2 is the 1 by 2 CH 1 minus 1 by 2. So, 1 minus 1 by 2 is equals to minus 1 by 2. Now, putting this value in the equation number 3, that means in this equation we put Q0 as, that means Q0 dash value we put in this equation. So, we can write Q0 is equals to Q0s plus 1 upon R1 H minus Hs. Here Q0s is nothing but the Q0 into Q0Hs represent, and 1 upon R1 is nothing but 1 by 2 CHs minus 1 by 2. This is a 1 upon R is nothing but 1 by 2 CH raised to minus 1 by 2. So, now substituting the value of Q0, this Q0 from equation number 4 into equation number V, that means in this equation we put the value of Q0, that means this value we put in this equation. So, we get equation number 1 as Q minus Q0 as minus 1 upon R1 H minus Hs is equals to A dH by dt. And now we give this equation as a equation number 5. Now, at steady state, the flow enter the tank equal to the flow leaving to the tank. We know at steady state the flow entering in the tank is equals to flow out in the tank. So, we can write Qs is equals to Q0s. That means this is the steady state value. Q0s is nothing but the QS. So putting this value in this equation, that means in this term Q0S we write QS. So we can write equation number 5 as A dH by dt plus H minus Hs upon R1, this term, and now from is equals to Q minus QS. This is a Q0S is nothing but the QS. And now introducing deviation variable, we introduce deviation variable as, that means in a Q minus QS is equals to capital Q and H minus Hs is nothing but the capital H. So we can write equation number 7 as, here we also consider this is a deviation variable, H is equals to H minus Hs, because also change in height. So we can write this equation as A d by dt capital H plus this H minus Hs is equal to H by R1 is equals to Q minus Qs is equal to Q. Now by taking Laplace of this equation, we can write A, and the Laplace of this derivation term is the S into H of S plus here H is the H of S upon R1 is equals to Q. Q is equals to QS. So this is a Laplace transform of this equation. So now H of S is the common. So we can write H of S in bracket AS plus 1 upon R1 is equals to Q of S. Now we rearranging this term, so we can write H of S upon Q of S is equals to 1 upon AS plus 1 upon R1. So we know H of S upon Q of S is nothing but the transfer function, and we can rearranging this term as the R1 is multiplied by this. So A R1 into S plus 1 and R1 go in the numerator term, so R1 here. So H of S upon Q of S is equals to transfer function, and now we compare this equation with first order general equation. So we get tau p is equals to AR1 and Kp is equals to R1, and we know R1 is nothing but 2Hs raised to minus 1 by 2 by C. This value we get by this. We know the 1 upon R1 is equals to 1 by 2 CH raised to minus 1 by 2, CH raised to 1 by 2. So from this we get this equation R1 is equals to 2Hs minus 1 by 2 upon C. So this is the second order. Now the graphical representation. So here we show this is a non-linear resistance present here. So this is a non-linear relation between the H and Q0. So this graph is non-linear. This Q0 is equal to CH raised to 1 by 2. But at a steady state value, that means at Hs and Qs, this follows some linear relation. This tangent is present. So we can say from the graph, the resistance R1 is the reciprocal of the slope, the tangent line passing through the point Q0HS. That means here tangent line, the slope of this. And also from this graph we can say, from the graph it should be clear that the linear approximation improve as deviation in H becomes smaller. That means the value of H is smaller, than the linear relationship can be improved. So this is a non-linear first order system. Okay. So in this lecture we study about the first order non-linear system. Now in next lecture we will study about the second order system. Okay.